Hello everyone, I am going to conduct a lecture series on antenna. Antenna are required everywhere. For example, any wireless communication. We cannot be able to communicate to each other without antenna. I am Mr. Asst Barkade from Department of Electronics, Institute of Science, Satara. In this lecture series, at the beginning, I would like to complete introduction and types of antennas. These 2 points should be complete in this first lecture. So, let's begin with the definition of antenna. We all know that a communication cannot be complete without antenna. So, definition of the antenna. There are different types of definitions are present for the antenna theory or for the antenna device. Now, according to the Webster's dictionary, antenna means a metallic device which is used to radiating or receiving radio waves. The simple statement is that a usually metallic device, it can be a rod or wire for radiating or receiving radio waves, means antenna. Similarly, another one agency, that is IEEE. IEEE define that antenna or aerial as a means for radiating or receiving radio waves. The definitions defined by the two agencies are too much similar. The main part is the radiating or receiving radio waves. This is the main working of that particular device. In other word, antenna is the transitional structure. Antenna is the transitional structure between free space and guiding device. Now, this can be seen into the diagram. See carefully. This is the transitional structure of the antenna. In that particular diagram, you can see that this antenna is placed in between transmission line and radiated free space wave. Now, a transmission line which is used to interconnect source and antenna, and a source is used to provide input to the transmission line, and these all three devices gives output a radiated free space wave. So, the guiding device, transmission line, the guiding device, this is transmission line or guiding device. So, guiding device or transmission line may take the form of coaxial line or hollow pipe waveguide, and it is used to transport electromagnetic wave from the transmitting source to antenna. This is source and this is antenna, from source to antenna. Now, another one is from antenna to source. For example, this guiding wave can be transmit signal from antenna to source once again. That means the working of transmission line is vice versa. It can be carried data from source to antenna, or also it can be carry data or electromagnetic signal from antenna to transmission line. Now, a transmission line, Thevenin's equivalent of the antenna system, for this figure is given into the this is the transmission line. This is the transmission line, Thevenin's equivalent of the antenna transmitting mode. Now, the load resistance RL. This is the load resistance RL is used to represent the conduction and dielectric losses associated with antenna. Also, according to this figure, where source is represented by an ideal generator, the transmission line is represented, this is transmission line, and transmission line is represented by a line with characteristic impedance ZC. Now, the antenna is represented by a load that is ZA, and now ZA is equal to RL plus RR plus J into XA, which is connected to the transmission line. Another one is, this is the load resistance, and the load resistance is used to represent the conduction and dielectric losses associated with that particular transmission line or antenna structure. While your RR is referred as to radiation resistance, and it is represent radiation by the antenna. That means radiation resistance. Now the last one is, that is XA. Now XA is used to represent the imaginary part of the impedance associated with the radiation by antenna. Now, what is exactly XA? It can be discussed in next few lectures in details. Before that, under the ideal condition, the energy generated by the source should be totally transferred to the radiation resistance RR. That means the generated energy should be transmitted through the radiator resistance RR. Also, which is used to represent the radiation by the antenna. However, in a practical system, there are conduction dielectric losses due to lossy nature of the antenna, due to lossy nature of the transmission line and also antenna, as well as those due to the reflections, that is mismatch of the losses at the interface between the line and the antenna. Now, taking into the account into the internal impedance, taking into the account the internal impedance of the source and neglecting line and reflection losses, maximum power is delivered under the conjugate matching. Now, what is the conjugate matching? the another one separate session will be present on that particular conjugate matching. Now the reflected wave from the interface create along with the traveling wave from a source toward the antenna. That means this is the wave which is transmitted from the source toward the antenna. And another one, a reflected wave is present which is transmitted from this antenna to the source, and by the way using combination of these two waves it's used to generate a standing wave. Now the reflected wave from interface create, that means reflected wave create a interface along with the traveling wave from a source toward the antenna, and constructive and destructive interface patterns are referred to as standing wave. Inside the transmission line, which represent pockets of the energy, concentrations and storage, typically resonant devices. A typical standing wave pattern is shown is here by using dashed lines in that section, that is transmission line. This is your standing wave. Now if the antenna system is not properly designed, the transmission line could act a large degree as an energy storage element instead of as a wave guiding and energy transporting device. That means if it is not designed properly, it could not be act as an energy transmission device. Instead of energy transmission device, it work as an energy storage element. So if a maximum field intensities of the standing wave are sufficiently large, they can cause arcing inside the transmission line. The losses due to the line, antenna and the standing wave are undesirable. The losses due to the line can be minimized by selecting low loss line, while those of the antenna can be decreased by reducing the loss resistance represented by this area. In this particular figure of transmission line Thevenin's equivalence of antenna in transmitting mode, this standing wave can be reduced and the energy storage capacity of the line minimized by matching the impedance of the antenna to characteristic impedance of the line. That means impedance of antenna and impedance of this line should be matched to each other. Now this is the same as matching load of the transmission line where the load is antenna, and it can be discussed in another one lecture separately, because this is the very big concept of impedance matching or load matching. So we will discuss into the separate session. Now according to the figure 1.2, it is used to represent the antenna system in receiving mode only, where source is replaced by a receiver. Now this same diagram, this same structure can be used as a represent as a receiving mode. Only the source can be replaced by using receiver mode, or it can be replaced by using simply receiver. All other parts of the transmission line remains same. The radiation resistance RR is used to represent the receiving mode and the transfer of energy from free space wave to the antenna. Simply, both equivalent circuits are same. Only source and receiver can be replaced with each other, and opposite mode can be designed. Now, before going to the types of antenna, in addition to this, to receiving or transmitting energy of antenna in an advanced wireless system is usually required to optimize or accentuate the radiation energy in some directions and suppress it in others. Thus, antenna must also serve as a directional device in addition to probing device. Okay, that means antenna can be provide a direction to your bird signal. So it must take various forms to meet the particular need at hand, and it may be piece of conducting wire, an aperture, a patch, and assembly of elements. For example, arrays, reflectors, a lens, and so on. For wireless communication system, an antenna is one of the most critical component. A good design of the antenna can be relax system requirement and improve overall system performance. A typical example is a TV. The TV is present in home, at every home TV is present. So a typical example is TV, for which overall broadcast reception can be improved by utilizing a high performance antenna, that is your dish antenna. The antenna serves to communicate system the same purpose that eyes and eyeglasses serves to a human. So what is the main objective of the antenna? So antenna is used to receive or transmit signal. It can be receive signal, weak signal as well as strong signal. The example is that your eyes and your eyeglasses. The working of eyeglasses for your eyes is that the strength of signal is increasing. Similarly, antenna is used to increasing the strength of signal, and it gives to the receiver of the TV. So, the field of antenna is a dynamic and vigorous, and over last 60 years of technology has been indispensable partner of the communication revolution. Many major advances that occurs during this period are in common use today. However, many more issues or challenges are facing us today, especially since the demand for the performance are ever greater. Many of the major advances in antenna technology that have been completed in 1970 through the 1990, those that were underway in the early 1990s, and signals of future discoveries and breakthroughs were captured in the special issue of the proceeding of the IEEE devoted to the antenna. So this was a volume of the IEEE which is totally based or totally devoted to the antenna. This introductory paper of this special issue, provides a carefully structured, elegant discussion for the fundamental principle of radiating element has been written as an introduction for the non-specialist and a review for the experts. Before going to the types of antenna, I would like to say that for the study of antenna, we are using, or I am using a book which is written by Balnis and name is Antenna Theory. So students, I will suggest you that you can refer the book which is written by Balnis for this particular antenna study. So let us go to the next point, and this point is the types of antenna. According to our syllabus, according to our structure, there are 6 different antennas are present in our syllabus also. So these are the 6 different types of the antenna, in which first one is wired antenna, wire antennas. Second one is aperture antennas. Third one is microstrip antenna. Fourth one is array antenna, and fifth one is reflector antenna. Sixth one is lens antenna. These are the different types of antenna. Now we will see these antennas one by one in details now. First antenna is wire antenna. Now the wire antennas are present everywhere. Wire antennas are familiar to human because they are seen virtually everywhere, on automobiles, buildings, ships, aircrafts, spacecrafts, and so on. Also, there are various shapes of wires antennas, such as straight wire, that is dipole, loop, helix are present, which can be seen in this particular diagram, in which this is your dipole antenna, which is a straight wired antenna. This is a circular loop antenna, and third one is the helix antenna. That means a shape like a spring and it is fixed to a dipole antenna. That means this is your helix antenna, and these are the wire antenna configurations. Now, loop antennas need not only be circular. I am showing that this is circular. It may be square, it may be circular. So it need not be circular. It can be rectangular, it can be square, it can be ellipse, or any other many configurations. The circular loop is the most common because of simplicity of the construction. Now, the second one is the aperture antennas. The aperture antennas may be more familiar to the human today than in the past because of increasing demand for more sophisticated forms of the antenna and utilization of the high frequency. Some form of the aperture antennas is shown in this figure, in which specially there are 3 different types of the aperture antennas are present. First one is pyramidal horn. It looks like pyramid. Second one is conical horn. It looks like conical. And third one is a rectangular waveguide antenna. So these are the different configurations of the aperture antennas, in which antennas of these types are very useful for aircraft, spacecrafts applications, because they can be very conveniently flush mounted on the skin of the aircraft or spacecraft. In addition, they can be covered with a dielectric material to protect them from hazardous conditions of the environment. So these are the aperture antennas. Today we are discussing in short every antenna. Today we are discussing in short. For every antenna there should be a separate session for the in detail discussion. So we are going to the third types of the antenna, that is microstrip antenna. Microstrip antennas become very popular from 1970. Today they are used for government, commercial applications. These antennas consist of metallic patches. Metallic substrate or a metallic patch on a grounded surface, grounded substrate. The metallic patches can be many different configurations. It can be seen in this particular diagram, in which first patch is square, second patch is rectangular, dipole, circular, elliptical, this is the triangular, this is the dish sector, and circular ring again, and ring sector. These are representing or representative shapes of the patch elements. These are most popular because easy of analysis and fabrication. Their attractive radiation characteristic also, especially low cross polarization radiation. The microstrip antennas are low profile, comparable to planar and non-planar surface. Simple and inexpensive to fabricate using modern printed circuit technology. Mechanically robust when mounted in rigid surfaces. Compatible with monolithic microwave integrated designs and very versatile in terms of resonant frequency, polarization, pattern and impedance. These antennas can be mounted on surfaces. See, these antennas can be mounted on rigid surfaces compatibly with monolithic microwave integrated circuits. This antenna can be mounted on surface of the high performance aircraft, spacecraft, satellites and missiles, cars, even handheld mobile telephones. They are look like this diagram. See carefully. This is a rectangular or square patch. This is a rectangular square patch which is placed onto the metallic substrate, which is connected to the ground plane, and this is the patch with T is the thickness, W is the width of that particular patch, L is the length of that particular patch, and H, this is the H is the height of that substrate. Also another one is the circular patch. Now the circular patch is with its radius, that is the radius of that particular circular patch is A, and thickness of circular patch is T also, and H is the height of that particular substrate. Now ER is the dielectric constant of that particular substrate, that is the relative dielectric constant of that particular substrate material. Now we are going to our next antenna, that is array antennas. Array antennas are used in many different applications. For example, many applications required radiation characteristic. that may not be achievable by a single element. It may, however, be possible that an aggregate of radiating element in an electrical or geometrical arrangement will result in desired radiation characteristic. The arrangement of the array may be such as the radiation from the element adds up to a given radiation maximum in the particular direction or direction, minimum in others, or otherwise desired. Typical example of array antennas are shown into this diagram, in which 4 different typical array configurations are defined, in which first one is YCIS antenna, second one is aperture antenna, wire antenna, aperture antenna, third one is microstrip patch antenna, fourth one is slotted waveguide antenna, in which usually the term array is reserved for an arrangement in which individual radiators are separate, as shown in this figure 1.c, that is A to C. However, the same terms is also desirable, and assembly of the radiator mounted on the continuous structure is shown into the figure D. Now, this is your Yagi-Uda antenna, in which there are 3 different elements are present. First one is reflector element, second one is feed element, and third one is number of directors are present in that particular antenna. Second one is aperture array antenna. In aperture array antenna, we can see that there is a rectangular arrays are present. Now microstrip patch array antenna. We had discussed that what is the patch antennas. Now array antenna. Now number of different patches are placed on a single substrate. That means this is microstrip patch array antenna. And last one is slotted waveguide. Now a single substrate, there are number of slots are present. So it is a slotted array antenna. Fifth one is reflector antenna. These are the different types of the reflector antennas. There are mainly 3 different types: parabolic, reflected with front feed, parabolic reflected with Cassegrain feed, and corner reflector. These are the 3 main reflector antennas. Now the success in the exploration of the outer space has resulted in the advancement of the antenna theory, because the need to communicate over great distances, sophisticated form of the antenna had to be used in order to transmit or receive signals that had to travel millions of miles. A very common antenna for such applications is a parabolic reflector antenna. This is parabolic reflector antenna, which is shown in this figure. Now antennas of this type have been built in diameters as large as 305 meter. So we can see that each and every reflector antenna has 2 different parts. First one is reflector, second one is field. See, in parabolic front field antenna, reflector is present and also field is present. These 2 elements are most important in the radiation of the signal from this antenna. Also there is the reflected and field are present at the same side. There is reflected and field are present in opposite side with the front field parabolic antenna, but with Cassegrain field parabolic reflector antenna, the reflector element and the feed element are present at the same side of the antenna, and another one additional part is the subreflector of that particular cascading feed antenna. Then third one is corner reflector antenna. Feed element and reflecting elements are totally opposite to each other, and this is the corner reflector antenna. Now, last one is the lens antennas. Now, number of people are using eye lenses. Now, purpose of eye lenses is that the picture should be clear for your eyes. The strength of picture should be clear when it reach at your eyes. Similarly, lens antennas working. Lenses are primarily used to collimate incident divergent energy to prevent it from spreading undesired direction. By properly shaping the geometrical configuration and choosing the appropriate material of the lenses, they can transport various forms of the divergent energy into the plane waves. They can use it in the most of the same applications as are parabolic reflector, especially at the higher frequencies. Their dimensions and weight becomes exceeding large at the lower frequencies. Lenses are classified according to the material from which they constructed. According to their geometrical shape, some form of the lens antennas are shown in that particular figure. Now, there are 6 different lens antennas are present in that particular lens antennas, in which first one is convex plane antenna. First one is convex plane antenna. But now lens antennas with index of reflection which is greater than 1. There are again 2 different types, and another one is lens antennas with index, refractive index of each n is less than 1. That means index of refraction is greater than 1 and index of refraction is less than 1. Now, when refractive index is greater than 1, then there are 3 different structures are present, and when less than 1 there are 3 different present. When greater than 1 there are convex plane, convex plane, then convex concave plane. And when refractive index of that particular material or that particular antenna is less than 1, at that time the concave plane, concave plane and concave convex plane, these 3 different antenna configurations are present into the lens antenna. So that's it about the antenna. In today's lecture we had discussed introduction of antenna, simply different definitions of the antenna, in which especially I am saying that the antenna is defined by the Webster's dictionary, antenna is defined by the IEEE standard, antenna is a medium, that is a radiating device of the energy from source to destination or that is pre-space, and it can be used to interconnect pre-space and source. These are some definitions. Antenna is used to radiating or receiving energies, radiating or receiving electromagnetic waves. These are some definitions. Now, next point was types of antenna, in which we had discussed a number of different antennas in short, in which specially 5 or 6 antennas are present, in which first antenna was wired antenna, second antenna was aperture antenna, third antenna was microstrip antenna, fourth antenna was array antenna, fifth antenna was reflector antenna, and last one antenna was lens antenna. So these are the different types of antennas. Now, students, I would like to say that for this study of antenna, you can refer antenna theory and analysis and design, which is written by the Balnis. So I would like to refer many number of books in next lecture. In next session, I will suggest you another some books. So if this book is available in your library, you can use this book. Thank you.